everyone. So this is going to be the 2018 AP Physics C Mechanics free response question. I'm going to start off with question one. So let's get down. Remember, question one is always that motion question, kinematics and dynamics. So this is actually a perfect example of the experimental design type questions that they have. So let's see. For part A, all right. They want us to figure out whether or not the value that we ended up calculating is going to be greater than, less than, or equal to the actual value, based off the fact that uh, the timer starts a little bit before. Yeah. So the electromagnet that's released in the sphere drops a little bit after the timer begins. So that means that when we do our calculations, the time measurement that we have is longer than it's supposed to be. So if we do this, our experiment is using the height and g to find time. So we're basically using this equation. Oh, let me actually write the generic equation first. So we're using the annoying x equation. The A lot of those terms we can actually just completely ignore because they don't matter. So this is going to be set equal to this. If I rewrite this, so I'm solving for g, so 2h over t squared. Okay, so you'll see why I want to do this. The reason I'm writing it like this is because I need to see a relationship between g and t. You could try to answer this in, I guess, more conceptual way, but I think the easiest way to visualize it is look at the equation, work it out, and then ask yourself what's going to happen to this if I increase t. Since t is at the bottom, and we're trying to see how g changes, this is an inverse relationship. So increasing the time means that this is going to be lower. So we're going to end up having that the g value is actually going to be less than the actual g. And for the most part, the explanation that goes with this could be anything. This actually would be somewhat of a decent explanation, like getting to this and then making the comment that since acceleration is proportional to 1 over t squared, they have an inverse relationship. Therefore, if the time measurement is longer than it's supposed to be, then the acceleration is going to be smaller than it's supposed to be. All right. Now, for part B, they want us to figure out a way to get a straight line. So this actually goes back to this equation that I have. Um, this is actually a really common question that they like asking. You need to know how to linearize data. So a lot of times they'll give you data, and if you were to graph it the way they provide it, it won't give you a straight line. Uh, if you have a graphing program, that's not too bad. Like you can do a quadratic fit to it or some sort of curve fit to it and get your equations from there. But when we're doing it on paper, we don't really have access to quadratic curve fitting tools. So we need to linearize this. We need to make it so that we have a straight line. Based off of the fact that h equals 1 half gt squared, from the kinematics equation, I'm going to end up having a curved exponential graph. So what I can say is, since my terms are h and t, if I just replace the t with t squared as my variable, let me call it, let's just say that this is, 5, just for convenience sake. If I just replace that with some term that's replacing the whole t squared, I'll end up getting a straight line. So this is a straight line, this is a curved line. So what they are going to want me to do is, on the vertical axis, I'm going to have h, and on the horizontal axis, I'm going to have delta t squared. I think they're going to want us to include the units. Yeah, label each row, include the units. This is going to be second squared. This is going to be meters. I don't think I need to alter h, so I'm just going to put it here. Delta t squared. My writing's really bad. So now I have to actually do the math for all this. 0.011, 0.045, 0.117, 0.161, and 0.203. All right. Now down here, honestly, a lot of these questions follow a very similar pattern. So now that I have my new data points, I need to, actually, before I move on to that, I should point out the point distribution. This was a 2 point question. So you got 1 point for this comment and 1 point for basically making some sort of reference to the fact that there's an inverse relationship to them, or some reasonable explanation of why having a higher time leads us to having a lower acceleration. And remember, when you do this, if you end up getting the choice wrong, the whole question is wrong. So if you said anything else besides less than, even if you did make a comment about it being inverse, you don't get the point. For part B, let's see, this was a 1 point question. Yeah, so this is 1 point, but you ended up having to do all of this stuff. So you had to make sure that you included this and included this. So a little unfortunate that all this work for 1 point, but it's a fairly easy one. All right, part C. So we're going to end up plotting this stuff onto the graph. So we'll have to do include units. Make sure that you read the questions. So this will be h meters. This will be delta t squared, second squared. Let's see, the time is going to go all the way up to about 0.2. So this could be 0.05, 0.1, 0.15, 0.2, 0.25. And then the height goes all the way up to 1, so this could be 2, 4, 6, 8, 1. All right, so going through these points, 0.1, and this is going to be really hard to read. 0.1 and 1, so that'll be right about there. 0.2 and 0.45. 0.6. And the last one, 0.203. All right. So this is what my graph will look like, and then line of best fit. Oh, that is not a line of best fit. Probably want to move this lower part down a little bit more. There we go. All right, so that would be my line. And let's see. Let's see. Scale, label axes, draw a line of best fit. Okay, so this entire thing was worth 4 points. So 4 points. Um, 1 point for basically getting the scale down so that you have more than half of the grid filled up. 1 point for the labels and making sure that they're consistent with what you wrote up here. So even if you messed up this and you, for some reason you said you would get a straight line doing H and T, you would still at least get credit for this since it made sense with what you did with part B. You get 1 point for plotting the data, again, based off of what you did up here. And then you get 1 more point for drawing your line of best fit based off of the data. So yeah, that's pretty much how that one is. I felt a fairly reasonable type question. All right, now for part D, it says it wants us to find the value for G. So what I can do is I can look at my equation from before. So my equation is H equals 1/2 G T squared. I know that if I take the slope of of a line, it's doing delta y over delta x. So my y value is h and my x value is t squared. So slope is essentially going to be h divided by t squared. Well, if I look at this equation and I write it as h divided by t squared, I have on the remaining, on the other side, 1/2 g. So what I can say is slope equals half g. So if I can find the slope of this line, I can then set it equal to half of the value of g and then just solve for g. So let's see. Let's pick a point. That's a really good point right there. And we'll do that point. That'll be fine. So slope is change in y over change in x. So my y value change is point, let's see, 0.68 minus 0.4 divided by, what would that be? 0.14 minus 0.08. So putting this in, 0.68 minus 0.4 is 0.28. 0.14 minus 0.08 is 0.06. So this is just 28 divided by 6. So my slope is 4.67, and then that's equal to 1/2 of g. So solving this, I can find that the g value that I have is 9.3 meters per second squared. All right, so this was worth 2 points. So you got, so this was 2 points. You got 1 point. Oh, you got 1 point for doing the slope, and 1 point for basically recognizing that you have to double the slope to get the acceleration. All right. Let's see. The next part, part E, they want us to derive an expression for the velocity as a function of time given this stuff. All right. So this is where the calculus comes into play. So they tell us that the position equation is given by this quadratic, which makes sense. I mean, that's kind of what the annoying x equation is. V naught t plus 1/2 at squared. So now what I have to do is rewrite this so that it's now for velocity. I actually could realize that some of the that this is essentially my acceleration. This is my initial velocity, or this is 1/2 the acceleration, and that this is my initial velocity. So I actually could get away with saying this and then saying that the initial velocity is negative 0.524 plus this is half of A, so doubling 5.75 gets me 11.5 T. So I could say that, but let's actually show, the calculus part. So if you remember, velocity is the time derivative of position. So derivative of position with respect to time. So I'm taking the derivative of AT squared plus BT plus C. If you recall, for polynomials like this, we take the exponent, multiply the coefficient by it, and then subtract 1 from the exponent. That's exponent is 1, so it just becomes B. Subtract 1, it gets rid of the term. And then C is just 0. So my velocity is going to be 2AT plus B. Plug in the numbers in. A is 5.75. And B is 0.0524. And look at that, we get the exact same equation that I got over here. All right. This was let's see, this was actually only worth 1 point. You could have actually done either way. So this was 1 point. You could have did the short way that I did here, or if you wanted to, you could actually use calculus. So this was actually a great example of where you didn't really need to do calculus. For part 2 of this, they want us to find the new value for G. So what I can do, I actually have two options. I can take the derivative of this velocity equation, because remember, acceleration is the time derivative of velocity. So I'll be doing the derivative of 2AT plus B with respect to time. The B drops out, and I'm left with basically 2A. And I could plug in A again, 5.75, to get that this is going to be 11.5 meters per second squared. I could do a similar trick that I did last time, where I either compare this equation to the kinematics annoying x equation and say the same thing, that this is equal to A, and then say, since A equals 5.75, which equals 1/2 A, then that means little a has to equal 11.5. I could have done it for this. Basically, I have a few different ways of doing this. Oddly enough, this was actually worth 2 points. So there was 1 point for realizing that it was going to be 11.5. And then the other point was doing one of these two methods, either doing the derivative of the velocity or doing this, comparing the equation that they give us to one of the other kinematics equations that we have, and then using that to figure out the acceleration. Part 3, they want us to find the percent error. That's actually not too bad. That's something that even a Regents kid can do. So percent error is the difference divided by actual times 100%. So our numbers are 11.5 minus 9.8. Actually, let me see. 9.81. Not like it really matters, but just to be safe. All right, so 11.5 minus 9.81 is 1.69, divided by 9.81 is 0.172, times by 100%, gives us a percent error of 17.2%. Um, Honestly, this was a really easy one, which is why this one was actually worth only 1 point. All right, so the last part, they give us this initial height and they want to find the speed right before it lands on the pad. So I could do a few different ways. I can use this equation I have to find time, and then use that into this equation for the the one that we just got for part one, to find the final velocity. I could do that. The only issue is that I'm going to end up with having to solve a quadratic. I don't want to do that because I just don't have the room right now, the way I'm writing this up. But honestly, on a test, that's probably what I would have done. What you could do, though, is realize that this equation still holds true, since the situation that we're dealing with here, that's being given to us, is a constant acceleration setup, which is why we can constantly model the equations with what we see. If for some reason this equation was not a quadratic with t squared, but was instead something like t cubed, or maybe there's a cosine or an e term or an ln term or something weird like that, I would not be able to make the same claim, and I would have had to do it the way I said before of using the given position equation, find the time, then use the derived velocity equation that we found to find the final speed. But since these two equations work for a linear constant acceleration, I shouldn't say linear, but a constant acceleration, then I can actually pull out this third equation, which is also for a constant acceleration. So when I do this, I can just kind of compare. Again, seeing as when I took the derivative, I got this as my initial velocity, I can plug that in for v naught, square that. Again, this is my acceleration, 11.5, and the d is 1.4. So I'm going to end up having 0.524 squared plus 2 times 11.5 times 1.4. So that ends up being 32.5, which gets me a final velocity of 5.7 meters per second. This question was worth 2 points. And there was actually, so they wrote 3 different ways that you could have put this in. The point distribution was essentially, well, if you use this method, it would have been 1 point for recognizing this, getting all these values from the previous parts, and then you would have gotten 1 point for this. If you instead had used the route that I mentioned before of finding the time using the position equation, you would have gotten a point for finding the time, and then the second point would have been for plugging it into this velocity equation. And the third route would have been to use conservation of energy. It pretty much works the same way. For those who don't know, this equation right here, the v squared equals v naught squared plus 2ad, this actually is a constant. This is a conservation of energy equation. You can check that out yourself. Just do it for potential plus kinetic equals kinetic. But what you end up finding is essentially the same idea, is that the you get 1 point for recognizing that these are your values, and 1 point for using conservation of energy to get your answer. So either way, this was worth 2 points altogether. So that was it for this one. Honestly, Really straightforward. You honestly didn't need any calculus, though some of the questions probably would have been a little bit easier had you known it. But that's it. Like I said, very typical experimental design where you're expected to figure out how to linearize data, and you should know the relationship between variables. So this is actually something I would definitely recommend that you go through and practice, because not only does it help with the APC, if you're taking the AP1, it also helps with that as well. All right. If you have any other questions, feel free to let me know. Otherwise, good luck and have a great day.